right, time for draftphysics.com, debatephysics.com. But physics doesn't do much rational debating now or even in the past. So we'll go over some of the de Châtelet, Madame de Châtelet, and the person who reinvigorated, let's say, or she won the argument in the end. In the sense of this debate about the nature of energy and the difference between the Huygens view, really, and the Newtonian view of energy. And it's turned into the Leibnizian, but again, Leibniz was basically just plagiarizing Huygens, as it turns out. But whatever. The facts are messy in terms of the historical record. So this whole de Châtelet thing is interesting. I mean, she died at 40. She was wealthy, tutored, an educated woman, knew multiple languages, translated people's scientific works. She made her own musings on some scientific subjects, but the one subject where she actually did some experiments, which they really don't highlight here at all, in the Wikipedia page, of course, to demonstrate that mv squared is what's conserved, that's the correct understanding of how energy works, that twice the force, four times the energy kind of thing, that's quadratic. And the Newtonian view that no, it's just pretty much momentum runs the universe and there isn't any other source of energy. And so with that kind of a context, I guess I could say more. Look, the whole thing is a soap opera. So she gets into an arranged marriage when she's 18 to some guy who's 37. They have 3 kids. 2 of them die, one at 20, one at 4. And the one that survived was apparently gay and was guillotined in the French Revolution. And then she had one illegitimate kid who died 20 months after birth. So it's all very ugly, very sad. She died in giving birth to that illegitimate child. So she's, the whole thing was arranged marriages. It's all a big soap opera of relationships. So she's famous for being a muse of Voltaire's, however they want to put it. He found her entertaining. Let's just say he had great respect for a woman, boldly going and all that kind of stuff. He said that her only fault as a person was that she was a woman. Her only fault as a man was that she was a woman, kind of thing. So a great deal of admiration, even though he fundamentally disagreed with her on the subject of momentum and kinetic, and the Leibniz-Newton conflict, however you want to phrase it. And it was clearly about Leibnizians, okay? So even though it's Huygens' idea, it's represented as Leibnizian, okay? And she was tutored by a Leibnizian, and they don't say that in the Wikipedia page, but he sued her for plagiarism. And then there is some, in Voltaire's letters, there's one reference I can't find it again, but whatever. I mean, it's so hard to find stuff on the internet in, translations, where he stated that she had reduced her confidence in the MV squared thing before her death. But anyway, so she might be famous for something that she didn't believe in the end. But whatever. That's the whole way history gets all kinds of messed up. So we're going to deal pretty much with just the controversy part regarding kinetic energy. And that's really the only great contribution she made. So she right up to her death, was doing a translation of Newton's Principia in French, a French translation. And apparently it's a well-respected translation where she added some side notes here and there. I haven't found any document that actually highlights what she commented on, what she added. Um, but clearly, although she had a great deal of respect and admiration for Newton's physics, somehow she thought it was okay to think that he was fundamentally wrong about the most important subject there is, energy, which doesn't make much sense, frankly. I mean, it's hard to make any sense out of somebody saying, Newton, you're wrong about something so elemental, about how much energy there is in the universe. I mean, and hugely wrong, not a little bit wrong, but way the hell off. Okay, so with that as context, I don't know, there's so much you could add, but whatever. All right, in 1741, Châtelet published a book titled, so this is a year before she died, response to Madame blah blah blah. So she's making a response to a guy from the Science Academy who I can't find a good English translation of his argument to her. So, I tried to translate the French, but the computer doesn't do it very well. So anyway, so this guy, secretary of the Academy of Science, has published a set of arguments addressing her regarding the appropriate mathematical expression for forces. Okay. De Châtelet presented a point-by-point rebuttal to Marianne's arguments, causing him to withdraw from the controversy. Now, this whole idea of whether he withdrawed from something, he didn't have anything else to say, I guess, is the point. But whatever. The arguments are basically, just presumptive at this point. Well, in 1741, this is after the Clay experiments, okay? And obviously, without analysis, those are convincing, okay, superficially. It looks convincing. Now, they make the classic mistake here of misdescribing the Clay experiments, okay? They talk about how deep the things penetrate when it's the displacement that was 4 times, not the depth. So clearly it was just about denting clay. It wasn't about going into the clay. All right, and there's a huge physics problem with that experiment. So it's just like rolling things. You have to account for the variables, and these physicists don't account for simple, basic variables. All right, then they throw in this Immanuel Kant crap, published in 1747, Thoughts on the True Estimation of Living Forces. So again, Kant isn't a physicist. Focused on de Châtelet's pamphlet, and the secretary of the French Academy of Sciences, Kant's opponent, accused Kant of taking ideas from de Châtelet. So they're all accusing each other of stealing each other's crap, which is funny. All right, so anyway, so advocacy of kinetic energy. This is the important part. All right. Although in the early 18th century the concept of force and momentum had been long understood, so obviously there wasn't an understanding. There was 2 conflicting views. All right, and obviously the Newtonians were way ahead at this time. Okay, at this time, Newton's understanding of momentum was what people believed. The idea of energy as being transferable by different systems was still in its infancy. So again, it really, the idea is that it's really easy to transfer energy between same things. So like things transfer energies easily, but if one guy's got Japanese yen and the other guy's got American dollars, then the transfer isn't so easy. So if you're trying to transfer momentum from a large object to a small object, or from a small object into a large object, that's a mess, and would not be fully resolved until the 19th century. So there's no full resolution. So that's just such nonsense. They always do this, and would not be fully resolved. Like when they decided that work is force times distance, when it's force times time. So when they decided to say, yes, the Holy Ghost stays in the Bible, we must have a Holy Ghost. The story just isn't the same without the Holy Ghost. Until the 19th century, it is now accepted that the total mechanical momentum mechanical momentum, whatever that even means, of a system is conserved and none is lost to friction. So what could that possibly mean? Of course, all of it can be lost to friction. How can they even say something? It is now accepted that the total mechanical momentum of a system is conserved and none is lost to friction. So I guess you could argue that, yes, if you have a system that doesn't have any friction in it, then you can't lose anything to friction. If friction's an outside, if there's the only kind of friction that exists is some outside entity that's scraping against your system, whatever your system is. I mean, it just doesn't make any, it's a terrible sentence. Simply put, oh, this will be great, right? Yeah, they're going to put it more simply. There is no momentum friction. What could that mean? So anyway, so the idea would be is that, look, you could argue that in the object itself, the transfer of force can be complete, but in what system is that ideal ever realized? So the only place that I could imagine it is with electrons and protons. There's no sandpaper, there's no atmosphere, there's nothing to get in the way to take any of the energy out of the interaction, so the interactions are complete. There's a 100% transfer. Nothing leaks out of electrons and protons. And momentum cannot be transferred between different forms. All right. Simply put, there is no momentum friction, and momentum cannot transfer between different forms. What does that mean? Okay, and particularly, there is no potential momentum. So again, this whole idea that there's no potential momentum, so a spring doesn't have any potential momentum. I mean, they're saying this like, what are you talking about? I mean, this is just absolute nonsense. I mean, we know it's mass times velocity. And frankly, we know it has to be conserved. So what the hell are you talking about? And if you lose it, if something loses its mass and its velocity, you'll find it somewhere in the environment, as Feynman would tell you. I mean, it's somewhere. It doesn't go nowhere. It goes somewhere. All right. Anyway, Emily Nuthers. So Emily Nuthers. So they always bring up this Nuthers thing, as if this means something. Some sort of mathematical proof. There's no such thing. Later proved this to be true for all problems where the initial state is systematic in generalized coordinates. So again, these sentences are incomprehensible gibberish. What the fuck could that mean to a reader? Later proved this to be true for all problems where the initial state is systematic in generalized coordinates. Mechanical energy. So whatever, again, they're using this word mechanical energy. What the hell is mechanical energy? Kinetic and potential. So, it doesn't even make any sense either. The stream is flowing. My boat's on the side of the shore. Do I really need to talk about some sort of potential thing? There's just stream energy. The water wheel is above the water, and I lower the water wheel into the water. Is it complicated what's going to take place? No. The stream's going to lose energy. The water wheel's going to gain energy. I mean, whatever. Kinetic and potential may be lost to another form, but the total is conserved in time. So how can you lose it and conserve it? Does that make any sense? No, it doesn't make any sense at all. This is just such gibberish. So that whole paragraph is just such a steaming pile of crap. All right, the Châtelet's contribution was that, so she made no contribution. So this is just a big lie. There really wasn't any contribution. Leibniz had already talked about energy conservation, and certainly Huygens. So it's just bullshit to say she invented the idea of energy conservation, conservation of mv squared. I mean, Leibniz's whole point was that that's the point, that's the quantity conserved. Leibniz was saying the quantity conserved is mv squared. So this is not her, introducing the idea of conservation. She's just affirming Leibniz's theory. The Châtelet contribution was the hypothesis of the conservation of total energy. So again, there's no such contribution. It was already stated, 50 years earlier, as distinct from momentum. Yeah. So, and again, how's there a contribution here? She's saying somehow mv squared is conserved, not momentum. That's exactly what Leibniz said. So what the hell are you talking about? What's her contribution? There's no contribution here. All right. In doing so, she became the first to elucidate the concept of energy as such. So again, how is she doing any of that? What? There's no contribution here. There's nothing. She's just affirming mv squared. And it's not 1/2 mv squared yet. They haven't figured out that it's way off yet. And to qualify its relationship to mass and velocity based on her own empirical studies. So most of the studies were not her studies, okay? They were Gravesand's experiments. And her own studies were kind of simplistically stupid, dropping wooden things into water, and seeing how much, it agitates. And then the worst, in my opinion, is she let things fly into, she gave things momentum, had the thing hit a pile of sand, and based on how she measured how far the furthest bits of sand went, and then made the argument somehow because fast things make sand go further, that it's quadratic. And slow things make sand go less far. Well, of course it does. Of course it works that way. Slow things can't make sand go fast, okay? Only fast things can make sand go fast. It's just too silly. So instead of measuring the total movement of the sand, that is, how much mass was moved, okay, what average velocity, which would have been the fair way to compare them, she just measured the ones that went the furthest. Okay. Inspired by the theories of Gottfried Leibniz, she repeated and publicized. So there's no repeated of anything. Okay, so she's changing the subject from Leibniz to the Grandsev guy. So, okay, anyway, inspired by the theories of Gottfried Leibniz. So there was no theory. There was just a statement, frankly. Okay, Leibniz didn't back it up with anything but saying, well, of course, 4 pounds dropped 1 foot equals the same energy as 1 pound dropped 4 feet, right? We all know that, don't we? And, he never did the experiment. All right. She repeated and publicized an experiment originally devised by Williams Gravesand, Gravesand, in which balls were dropped. So let's understand, round things were dropped and dented clay. Didn't penetrate deep, just superficial dents. You can see the pictures the guy drew. They're just superficial dents in the clay, not even close to halfway into the clay. The round thing just dents the clay. All right. Were dropped from different heights into a sheet of soft clay. Each ball's kinetic energy is indicated by the quantity of material displaced. Now that's correct, but they said depth, how deep into the clay. That's what they say later. And it's not about how deep. That won't give you that 4 answer. That won't give you a quadratic answer, because it's really just about a round surface. All right. As indicated by the quantity of material displaced, was shown to be proportional to the square of the velocity. So if you dent something with a round surface, okay, so I guess I'll do this a little bit again. So nobody challenged any of this stuff with an actual physics argument, where they point out how, well, if you understand the real physics, this experiment is useless. It's not going to tell you the truth, because there are variables, facts, okay, that demonstrate it to be, useless mush. And you ought to pay attention to those. Let's see if I can move this successfully. Nope, that's the wrong thing. Maybe that's it. No, that's the wrong thing. Come on, one of these has to be the right. There it is. All right, so the idea is you're dropping a round object. And the key thing to understand about a round object is it has a flat side, okay, and then it has this vertical side. And so you could sort of represent that as being this part, the bottom part here, this lowest part of it is pushing straight down a lot, okay, and it's pushing sideways very little. And then this part, and this part especially, is pushing sideways a lot and pushing down very little. All right, and you can understand that, well, what's happening if you push down? Well, if you push down, the clay can't compress. It's pushing back up. There's increased pressure. And so it has to go this way and this way. So you have two motions you have to accomplish if you push down. You have to do two motions, where if you just push sideways, it's only one. So obviously you're doing less mechanical work. You're moving the clay less distance to get it out of your way. This is very easy to get the clay out of your way. This is a lot of work to get the clay out of your way. All right, so obviously when you're denting the clay, okay, denting the surface, the more shallow the dent, the more work you had to do. And the deeper the dent, the more of this you were doing, and the less of this you were doing. So this requires a lot of this. Okay, a little dent requires a lot of down. Big dent requires a lot less down because you're doing a lot more of this, okay, by percentage. So you're doing this, okay, 70% of the time, and only doing down 30%. Okay, where in this other case, where you're just denting it here, you're doing exactly the opposite. 70% down, okay, and only 30% this way. So those are just rough approximations. But I'm just saying that's the obvious flaw in the reasoning. Obviously, it gets easier and easier to penetrate the clay the further and further you go because you're pushing sideways more and pushing down less. Pretty easy to understand why the experiment isn't going to show you the truth. Alright, so it should also be pointed out that the Gravesend guy who did this experiment and didn't realize, frankly, the obvious flaw in it, also believed perpetual energy might be possible. He actually did travel the world going to any kind of guy who was claiming to have created a perpetual motion device, and he was quite interested. All right, anyway, in which balls were dropped from different heights in a sheet of soft clay. Each ball's kinetic energy is indicated by the quantity of material displaced, as shown to be proportional to the square of the velocity. She showed, so she didn't show anything, it's his experiment, that the balls that hit the clay with twice the velocity penetrated 4 times as deep into the clay. So that's not what she did. It doesn't go 4 times as deep. It only displaces 4 times the amount of volume of clay. That's the truth. Okay, that's what Gravesend illustrated, was displacement, not depth. So that sentence is just wrong. One of her most important contributions to science was her elucidation of the concept of energy and energy conservation. So here they said it again. She made absolutely no original statement. Okay, this was already a concept conservation. It was already, again, overtly stated by Leibniz. This is the quantity conserved, mv squared. That's in Leibniz's own words, so to speak. With the exception of Leibniz, earlier thinkers like Newton, with the exception of Leibniz and Huygens, as it turns out, earlier thinkers like Newton, I mean, to call Newton an earlier thinker is just so hilarious, especially when she's writing a translation of Newton, believed that energy was indistinct from momentum. So all the little assholes who keep saying that Newton was a Leibnizian, clearly Wikipedia doesn't think so. All right. and therefore proportional to velocity, and that's all it is, okay? Twice the force, twice the velocity. 3 times the force, 3 times the velocity. No quadratic increase in your energy. According to this understanding, the deformation of the clay should have been proportional to the time the ball spent falling. The fact is we know that that's twice the velocity. All right, so we know that if you drop it on a scale, you would get a different reading. You wouldn't get this quadratic increase. Okay, so it's just the fact that they're doing an experiment in a particular way. All right, if they allowed the balls to actually penetrate into the clay, they wouldn't keep that quadratic increase. As soon as both of these balls go past the halfway point, then it's a fair fight. And you're going to get 2 to 1, not 4 to 1. So as soon as both of them have gone past the halfway point, then they've equalized. Then they're doing 50-50. Then they've done the same work. All right, and that's the real key to the whole argument. So if they had done some physics and actually analyzed the experiment, the simple defect in the reasoning could have been found, but nobody was doing that. They were too busy revolutioning and doing all kinds of other things. Right, anyway. So that it's just so wrong to say she made any new statements regarding conservation of energy. With the exception of Leibniz, earlier thinkers I believe that energy, okay, right, and therefore proportional to the velocity. According to this understanding, the deformation of the clay should have been proportional to the time the balls spent falling. We know that's how it acquires its energy. So it's how long you fall in gravity will decide how much energy you've acquired. It's just an absolute fact. When in fact it is proportional to the height from which they were dropped. So again, it's not the truth. All right, and if they had done the experiment differently, they would have got a different answer. In classical physics, the correct formula is E equals 1/2 mv squared, which is just absolute crap. And then they're not explaining where the 1/2 comes from. All right, anyway, where the E is the kinetic energy of an object, m is the mass, and v is the speed. Energy must always have the same dimensions in any form. So whatever that means. So they're saying the same dimensions, they mean magnitude or strength or whatever, you know. They're saying they have to conserve 1/2 mv squared. And physicists will tell you, no, you have to conserve momentum, frankly. All right. I mean, it's just too silly. Which is necessary to be able to relate it in different forms. Which is necessary to be able to relate it in different forms. Where did they get this sentence from? What is this? Mush. Who could understand that sentence? Energy must always have the same dimensions in any form, which is necessary to be able to relate it in different forms. Kinetic energy, potential, heat. We know these different forms are just different forms of momentum. You can have a big thing moving, or you can have the little things moving. But it's all motion. It's all mass moving. The kinetic energy theory has momentum right in it, mv. It's right there in the middle of it. Anyway, Newton's work assumed, so again, it's just another cheap little shot, okay? Newton was meticulous in defending his arguments. He didn't really do assumption stuff. Anyway, Newton's work assumed the exact conservation of only mechanical momentum. There's no mechanical momentum. There's just momentum. So qualifying the word momentum with the word mechanical just makes no sense at all. mv, it's a mass moving a velocity. That's momentum. There's no non-mechanical form of that, is there? Can somebody describe to me a non-mechanical form of momentum? A broad range of mechanical problems are solvable only if energy conservation is included. So again, what does that mean? You can solve the equation so the 10-ton train, okay, I take a 5-ton train, I add 5 tons to it, I reduce its velocity in half, it loses half the kinetic energy but conserves all of the momentum. Now, how can you make that rational? You can't. All right. M, the mass, and the V is the speed. The energy must always have the same dimensions. Okay, we did that part. Mechanical, the broad range of mechanical problems are soluble only if energy conservation is included. The collision and scattering of 2-point masses is one of them. The collision and scattering of 2-point masses. They're basically just saying the interaction, the collision. And they're saying that somehow momentum doesn't have to be conserved, that kinetic energy does. And the Newton's cradle proves that's nonsense. All right. Leonard Euler and Joseph Louis Lagrange established a more formal framework for mechanics using the results of Châtelet. So it's clearly showing that this fake experiment by Châtelet, I mean, this kind of poor pseudoscience experiment, I mean, it's a bogus experiment. It's not showing 4 times the work. You're measuring it wrong. It's like rolling something, okay, twice the speed, 4 times the distance. Well, that's because it's half the friction. You know, it's only 2 seconds of rolling time. It's only twice, okay, the friction. It's only twice the work. Friction only does twice the work on the object. All right, so I don't think we need more on her death. But anyway, in 1749, the year of Châtelet's death, I thought she died in 42. Okay, my mistake. She completed the work regarded as an outstanding achievement, her translation into French with her commentary of Newton's Principia, often referred to as simply the Principia. Principia, yeah, it's close enough, including her derivation of the notation of conservation of energy. So again, there's no derivation. Leibniz already said it from its principles of mechanics. So it's just nonsense. Despite modern misconceptions, okay, so they're going to talk about somebody's misconceptions. The editors of Wikipedia are going to talk about modern misconceptions. Newton's work on his Principia was not perfect, so that's their statement. They're saying Newton was wrong, okay, and based on, because Leibniz said so, you know, based on an experiment they've never performed. Dropping 4 pounds 1 foot and dropping 1 pound 4 feet. They never did the experiment and found out how much the impulse energy is. They've never measured the impulse energy of those 2 events to prove that they're the same, because they're not. Her commentary was an essential to her contemporaries as her spreading of Newton's ideas. Right, so spreading Newton's ideas in the most bizarre, negative way. I can't even imagine Newton being other than appalled. Okay, that you would say an idea that is so central to everything he believed, you're saying was wrong. That he somehow didn't understand, okay, something as elemental as energy in the universe. Force. Newton didn't know what he was talking about, is what they're saying. Châtelet's commentary was very extensive, comprising almost 2/3 of a volume 2 of her edition. So they're talking about this extensive commentary, but I can't find the extensive commentary made to the translation. So apparently they haven't translated that into English. So what we need is an English translation of the French translation of Newton, where her commentary is included. So they're saying almost 2/3 of a volume 2 of her edition. So they're saying 2/3 of the second book of Newton's. She wrote commentary that is, you know, that Newton's book is like whatever, 300 or 400 pages. Let's see. To undertake and formulate projects such as this, Châtelet prepared to translate the Principia by continue her studies in analytic geometry, mastering calculus, and reading important works in experimental physics. In her rigorous preparation that allowed her to add a lot more accurate information in her commentary. So again, if somebody can find her commentary on Newton's Principia, I would like to see. I've seen her book, where she's writing a kid's book, okay, and that's just gibberish, about how we have free will and shit, and how wonderful God is, even though God killed her children. Yeah, he's a great guy. Both from herself and other scientists she studied or worked with. So they're really not talking about all the experiments she did. All right, anyway. She was one of the only 20 or so people in the 1700s who could understand such advanced math and apply the knowledge to other works, whatever knowledge that was. Okay, so that's an ambiguous statement. This helped de Châtelet greatly, not only with her work on the Principia, but also in her other important works like Institution de Physique. I think that's the kid's book. She wrote a book, okay, basically for teaching her son, the gay guy who got killed in the revolution. Anyway, de Châtelet made very important corrections in her translation that helped support Newton's theory about the universe. So isn't that just amazing? She helped support Newton's theories while she's ripping the heart out of Newton's theories. All right, Newton, based on the theory of fluids, suggested that gravitational attraction would cause the poles on Earth to flatten, thus causing the Earth to bulge outward at the equator. In de Châtelet's memoir, which confirmed Newton's hypothesis about the shape of the Earth and gave more accurate approximations. So I have to see that. Charnot discovered, I don't know why she's called Clarnot, discovered a way to determine the shape of other planets in the solar system. De Châtelet used Charlot's proposal that the planets had different densities in her commentary to correct Newton's belief that the Earth and the other planets were made of homogeneous substances. The guy, again, I don't know what Newton speculated, but I'm not too sure that Newton didn't know. I don't know when they found the red spot on Jupiter, but I don't think Newton thought every planet was made of exactly the same stuff. Just looking at the moon, you'd have to say, come on, it doesn't look quite right. Anyway, de Châtelet used the work. I mean, the whole idea that the moon crashed into the Earth is such an interesting theory. That the Earth was just crusted over, and those are the plates. And then the moon actually bumped into the Earth and left a big round blob on it. All right, and that big round blob ended up being on top of those plates, and it broke the plates, and that's just been moving around ever since. It's been, on the spinning Earth. It's been rotating slowly but surely, gaining momentum and flying apart. And it's such a nice theory. Anyway, de Châtelet used the work of Daniel Bernoulli. So one of the Bernoullis. No, that's a different one. A Swiss mathematician and physicist to further explain Newton's theory of the tides. So this is all kind of minutia. So it's, again, there's really nothing wrong with Newton's fundamental argument. The proof depended upon the three-body problem, which even the best mathematicians in the 18th century Europe were still confounded with. And it's always a problem. You're always just going to have to do an approximation, because every single time one thing moves, all the other things have to move differently because you've changed the environment they're in. Using Charnot's hypothesis about the differing of the planet's density, Bernoulli theorized that the moon was 70 times denser than Newton had believed. De Châtelet used this discovery in her commentary on the Principia, further supporting Newton's theory about the law of gravitation. So I don't understand how it supports Newton to point out Newton thought the moon was much heavier. I mean, obviously they hadn't figured out what the gravitational constant was yet, So mass is irrelevant to orbit. Orbit just cares about your velocity. So all Newton could do was tell you what the velocity of the object was. He couldn't tell you the mass of the object. Published 10 years after her death, today de Châtelet's translation is still the standard translation of the work into French and remains the scholarly complete rendition in French. So it's unfortunate that all these old documents aren't easily acquired in English. It really is kind of irritating. Her translation was so important that it was the only one in any language used by Newtonian expert, so says Wikipedia, Bernard Cohen, to write his own English version of Newton's Principia. De Châtelet not only used the works of other great scientists to revise Newton's work, but she added her own thoughts and ideas as a scientist in her own right. I wish, I don't even know why they do the stupid Latin thing, because frankly, these Latin translations do seem like they go all over the place. Her contributions to the French translation made Newton and his ideas look even better in the scientific community. So it doesn't make any sense. She's basically gutted a fundamental notion about the what is the essence of energy, and she squared it. I mean, a huge, giant difference. And they're talking about how, oh yeah, it was a great advance for Newton. No, it's not. No, you ruined Newton. You ruined physics, frankly, because it's just plain wrong. Okay, all their particle physics is wrong. I mean, because they didn't measure the mass of the electron right, because they used 1/2 mv squared to measure its mass. And around the world, in recognition of this, is owed to de Châtelet. So I would say yes, she's big on the blame list of doing shitty, cruddy little show experiments and doing really poor analysis and really bad logic and physics. So she is, it's her fault. Yeah, your physics, conventional physics sucks because a rich person doing crap science was confused to be a scientist. All right, anyway, this enormous project, along with the foundations of physics, proved de Châtelet's abilities as a great mathematician. So again, I don't see any of that. Her translation and commentary of the Principia contributed to the completion of the scientific revolution in France. So the revolution was a big failure, obviously, and to its acceptance in Europe. All right. So anyway, so yes, so she has this whole book she wrote about all this happiness crap, and again, this is while her children are dying. Okay. Life is just so great. Oh yeah, it is the most best of all possible worlds. Everything is just fine, blah, blah, blah. And they keep talking about this principle of sufficient reason, like this is somehow a rational concept. What the fuck is the principle of sufficient reason? Can I translate that into any language and somebody will understand what the fuck that phrase could possibly mean? Oh, anyway. All right, so in application, de Châtelet proposed that being happy and immortal are mutually exclusive. Oh, immoral, sorry. Being happy and immoral are mutually exclusive. So let's understand, they don't see any ethical crime in inheriting ownership of the world and having a bunch of servants. All right, that's not a moral crime of any kind. Okay, being an aristo. According to de Châtelet, this principle is embodied within the hearts of all individuals. Yes, all the fancy pants. Okay, and even wicked individuals have an undeniable consciousness of this contradiction that is grueling. Yeah, so yeah, you all felt so guilty, didn't you? As you use up other people's lives, you underpay them, you rip them off, you steal their labor. Oh, yeah, it's all fine. Okay. But we're worth it. We're so much better than they are. It suggests one cannot be living a happy life while living immorally. So she keeps, another word, what's the definition of a moral crime? Anyway, so just too disgusting. It's really just too. I inherited, you know, I earned it because I inherited it. Obviously, I'm better than them. I wouldn't be born with, inheriting all this wonderful stuff if I wasn't intrinsically and fundamentally better than everybody else. I mean, it really is just so disgusting. And like I said, in light of the bleak reality, I just don't even know how people could talk this shit, this life-affirming crap while you watch your kids die. Amazing glibness. I can't even imagine how depraved one's psychology has to be, to talk this shit about how wonderful everything is. Bible scholarship, oh dear. We might throw it in there. Châtelet wrote a critical analysis of the entire Bible. Oh, so she found the Bible unremarkable. But she was still an insufferable optimist. The synthesis of her remarks on the book of Genesis was published in English in 1967. Well, obviously she had to say something negative about the Bible for Voltaire to find her sufferable, I imagine. An essay on intellectual activity and whatever, and a book, her complete notes. So they don't really say anything about what the hell she did say. But what I've read of it is, girly bullshit, frankly. And it's Leibnizian, It's just a justification for somehow it's all the great mystery of God's great understanding of what's best. And it's best if your kids die brutally, because it builds character. Anyway, all right, so some institute was founded in her name and blah, 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 blah. But again, her family just, it was a train wreck. Just tragedy all the way down. No happily ever after, that's certainly for sure. All right, so that's probably enough. We just want to do the physics part, and I guess I hit enough of that to make the point. The arguments sucked. And the way they paraphrase things is just so wrong also. I don't even know. Like somehow Newtonians wouldn't realize that if a boat's moving and you dropped a cannonball, that the cannonball's already still moving and it drops straight down. Yeah. I mean, they do that kind of bullshit where they say somehow Newton didn't know that the cannonball's going to have the motion. It's already got the force. It's already moving in that direction. It's going to keep moving in that direction. Well, anyway, I mean, just terrible the way they distort the actual statements. Again, I mean, Newton couldn't have been clearer. The sentence right below his second law, he says, twice the force, twice the velocity. 3 times the force, 3 times the velocity. I mean, he couldn't make it any clearer. All right, anyway, so another crappy Wikipedia article and such. So when they do talk about, well, there's no point in nitpicking the little stuff, but, even the whole family, the legacy of her kids, they basically tell us that the same kid, they describe him dying twice. They say he died as a toddler, and they say he died 20 months later or whatever it was. I mean, it just doesn't make any sense. They almost imply like she had 5 kids and not 4. It doesn't make any sense. Anyway, so till the next time. The point is, she only had one that survived past what you would call maturation. But no explanation what any of them died from. Anyway, so till the next time, and such, and so forth, and whatnot. Yeah, it's enough. Might as well put this on the screen for the hell of it. Okay, Wikipedia is evil and stupid and moronic, and obviously the editors are emotional children. They can't tolerate somebody disagreeing with their authority because they're all proven experts. They've all proven themselves to know the truth. Yeah, pathetic.